we can actually use a power series to find a series for the derivative or integral of a particular function. So suppose we know that some function can be represented by the following power series, where the nth term is x to the n over n plus 1 quantity squared. Okay, so if we know that the function is represented by these terms, then we could just differentiate this term by term to get the derivative of that function. So for instance, if you differentiated 1, you would get 0. If you differentiate 1/4 x, you get a fourth. If you differentiate 1/9 x squared, you'd get 2/9 times x. 1/16 times x cubed would give you 3/16 times x squared, and so forth. And so if you look at the nth term, okay, well, we know that the n plus 1 quantity squared in the denominator is just a constant. So actually, if we just took the derivative of x to the n, we would get n times x to the n minus 1 for the nth term of the derivative. So therefore, we could actually write the derivative as another infinite series where we go from 1 to infinity, and then we would have this would be how we would represent these terms. So this series represents the derivative of the function. You could also calculate the integral of a function as well. So again, suppose we have a function here represented by this series where the nth term is -1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. Okay, well then on that one, if you integrate this, you actually would get a constant. So we're going to give you the constant first instead of last. And then if you integrate x, you get x squared over 2. And if you integrate x cubed, you get x to the 4th over 4. And then it's also times 3 factorial in the denominator. X to the 5th would be x to the 6th over 6. And that would be times 5 to the factorial in the denominator. And so forth. So actually, you can show that the nth term of this one could be represented by -1 to the n minus 1 power times x to the 2n over 2n minus 1 quantity factorial times 2n. So therefore, the integral of the function above could be represented by this series plus the constant. And so, you know, that's just one of the applications of power series, is if you have a function that maybe you don't know how to integrate or differentiate it, but you can write it as a power series, then you could just take the derivative or the integral of that power series to get the result. Okay, so here I'm going to show you how we can represent this function as a power series. Now, this function is actually very similar to the sum of a geometric series. And remember, the sum of a geometric series is a over 1 minus r. So if we were to let a equal 1, so there, that would be the a, and then let r equal x, then that would be right here. And so we could say this is actually a over 1 minus x. So a over 1 minus r becomes 1 over 1 minus x. And then we can represent this function, since we know what a and r are, then we can represent this function as the geometric series a plus ar squared, and so forth. Now, if we take this series and replace a with 1 and r with x, we would get, instead of a, we would get 1, and instead of ar, we'd get 1 times x, and instead of ar squared, we get 1 times x squared, and then 1 times x cubed, and so forth. So this series would actually could be used to represent this function 1 over 1 minus x. So basically it's the series where n goes from 0 to infinity, x to the n. And we showed earlier that this series converges as long as x is between -1 and 1. That was the interval of conversion. So this is an accurate representation of the interval, but it's only accurate over this interval of convergence from -1 to 1. Now, if we wanted to have a different interval of convergence, we could center this power series for 1 over 1 minus x at a different value. So let me just show you how we could do that. First of all, let's say I want it centered, instead of centered at 0 like we had up there, let's say it's centered at -1. Well, then you would actually need to replace the x that we used up here as, instead of x, you would have x minus -1 or x plus 1. Okay, then we can write the result as the sum of a geometric series. So what I'm going to do here is I'm going to replace x with x plus 1. Okay, now if you do that, that actually is not exactly the same as 1 over 1 minus x. So to keep it the same, I'll have to change this number to 2. So see, if I write this as 2, then 2 minus x minus 1 is the same as 1 minus x. But the key was getting this to be x plus 1 so that it's centered at -1. Okay, so now, but still, in order to get this into the form of the sum of a geometric series, I need to get it in this form, a over 1 minus r. So what I need is I need this right here, this 2, I need that to be a 1. So there's an easy way to make it a 1, just divide it by 2. So if I divide each term in this series by 2, there's 3 terms. Divide the 1 by 2, I get a half. Divide the 2 by 2, I get a 1. And then divide this sum by 2, I get x plus 1 over 2. Okay, so now I have a on top, that's my a, and then on bottom I have 1 minus r. So in this case, r would be x plus 1 over 2. Okay, so now I've written this function as the sum of a geometric series where a equals a half and r is x plus 1 over 2. Now if you go back to what I showed you here and write the geometric series a plus a times r plus a times r squared and so forth, then basically what you would have is you would have, well, I went ahead and distributed factored the half out, so the half is the a. So really this in here should be what? This should be a with the 1/2 factored out, so it's just going to be 1. And then this should be r, which it is. And then this should be r squared, which it is. Then this should be r cubed, which it is, and so forth. And then the nth term would be r to the nth power. Okay, now, so we know that we can write 1 over 1 minus x now as this series, this geometric series, a times r to the n, okay? But now, where does it converge? Well, to find where it converges, remember I have to take the absolute value of r and set it less than 1 to find the interval of convergence. And then I can solve that algebraically, multiply both sides by 2, and I get the absolute value of x plus 1 is less than 2, and then solve that absolute value inequality, and you get -3 to 1. So I didn't check the endpoints here, but I definitely know that I can represent this function as this series, and it's going to be accurate within the interval from -3 to 1. So to find a power series for 6 over 3 plus x, what I can do is I can divide this by 3 to make it a 1. So let's divide each term by 3 so that I'll get a 1. So 6 divided by 3 is 2, and then 3 divided by 3 is 1, and x divided by 3 is x over 3. And then to put that in the form of a over 1 minus r, let's change this to negative x over 3, and now I have a over 1 minus r, where a is 2, and r is negative x over 3. Okay, so now since I know a is 2, let's say I factor the 2 out of the expression, and then of course you remember this would be 2, then 2 plus 2 times r, then 2 plus 2 times r squared, and so forth. Well, if I factor the 2 out, the 2's out here out of the way, and then if you factor 2 out of 2, you get 1. But then the next term would have the r, which is minus x over 3. The next term, the r squared, which would be x squared over 9. The next term would be r cubed, which would be minus x cubed over 27. And so that's a way to represent that function as a power series, and it'll actually converge if you solve for when the absolute value of r is less than 1. And I solved that here. So the absolute value of x over 3 is less than 1, and then that just means the absolute value of x is less than 3, and then so the interval of convergence would be from negative 3 to 3. So this function can be represented by this series with an interval of convergence of negative 3 to 3. Now, there's a couple of operations here. And it says that if you have two series, a sub n xn and b sub n xn, and if you take this first series and you replace x with kx, then that would give you this new series, a sub n k to the n x to the n. And it also says that if you were to take the sum or difference of those two series, it would be the same as the series of the sum or difference of these two series up here. So it would be a single series of a sub n plus b sub n times x sub n, or a sub n minus b sub n times x sub n, where you're dealing with either a sum or a difference. And then the interval of convergence of the sum or difference would be the intersection of the two series here of their intervals of convergence. So it would be where the intervals of convergence of the two series intersect. So to find the series for arctan of x from negative 1 to 1, we can do this. We know that if we were to take the function 1 over 1 plus x squared and integrated that, we know that would be arctan of x. So let's assume that f prime is 1 over 1 plus x squared, so that f would be the arctan of x. Now f prime can be written as the sum of a geometric series where a is 1 and r is negative x squared. So therefore f prime can be written as 1 plus 1 times r squared plus 1 times r cubed, and so forth. And if you simplify that, f prime is 1 minus x squared plus x to the fourth minus x to the sixth, and so forth. And you can show that that converges as from negative 1 to 1. Now, if you were to integrate this, you actually would get these terms where the nth term is minus x to the n plus 1 over n plus 1. And since this represents this series, and we know when we integrate this function, we actually get arctan of x, then that series must actually be the arctan of x, and it converges from negative 1 to 1. And actually you can then show that it converges on the at the endpoints as well, plus or minus 1. Okay, so take a look at this next series, and I have the natural log of 1 plus x. So here, since I know if I integrate 1 over 1 plus t, that would equal to the natural log of 1 plus x if I integrate it with respect to x. So basically, I take this series and I integrate it, and I get my new series, and my new series is actually equal to the natural log of 1 plus x. I don't really have time to do this one justice, so pause the video and read the product of a power series here. But if you want to write 1 over 1 minus x quantity squared as a power series, what you would do is you would get the series for 1 minus x, and then you would multiply that series times itself. So here I have the series for 1 over 1 minus x, and here's the same series for 1 over 1 minus x, and then if you multiply those two series together, you get the series that we're looking for 1 over 1 minus x quantity squared.